of Ras Nouadhibou, which Nouadhibou comes from a Berber term. Berber is a language spoken by some people in Northern Africa. And so you can see here on this photo from the International Space Station, you can see on the lower left of that photo, a little corner of that space station, and it was taken about 250 miles away from the coast. So you can see on this photo the peninsula, and at the top of which is Nouadhibou. And Mauritania is basically a vast expanse of desert that is facing the Atlantic Ocean, facing towards the west, the Atlantic Ocean. And so Nouadhibou, it's a peculiar place, and it's known for a number of things. Among other things, it's one of the biggest ship graveyards in the world, where basically people have abandoned their ships there instead of disposing of them properly because it's cheaper. There's quite a bit of corruption that allow people to leave their ship on the shore. But unfortunately, it has also become one of the departure points for African migrants trying to reach the European Union. And they're hoping to reach the Canary Islands, which is part of Spain, which is indicated here by this arrow. And as I'll go back to this topic a little bit later, we'll see that in an oceanographic point of view, it's actually not a very good idea to start from this point to try to reach this point in the ocean. And so I never went back to Nouadhibou, but I really want to go back. But about 10 years ago, I went on a kite surfing trip in Morocco, in Western Sahara, in the town of Dakhla, which was just a couple of 100 miles from Nouadhibou. So I had a chance to go back. So a little bit fast forward, in 1999, I started my higher education and I studied engineering in Brest, in Brittany, at a French school called the École Nationale Supérieure des Ingénieurs des Études et Techniques d'Armement, which translates to something like Higher National School for Engineers of Studies and Techniques of Military Weapons and Equipment. So my school was basically a military school that, originally it was a military school that was training engineers for the French army, including the French Navy. 30% of my classmates, in my class of about 120 students, were officers in the army being trained for the army to become engineers. And some were effectively trained in weaponries and how to build like ships, but some of them were trained to actually, were trained in oceanography. And actually, it's not surprising because the navies of all the developed countries in the world have been basically the instigator of oceanographic research. It is a matter of knowing, the battlefield on which to navigate their ships, and it's a matter of life and death for the people that are fighting for different countries. So I went to that school because it was not only training engineering for the army, but also training engineers for, civilian students like myself. And so the curriculum was kind of like quite well-rounded in the sense that I studied both mechanical engineering and electrical engineering. And when you think about oceanography and the type of work that I do, it makes sense because you want to know about mechanics, you want to know about fluid mechanics, but you also want to know about the engineering of the instruments that are being used to study the ocean. But outside of the oceanographic topic, one of my favorite area of study was signal processing and the study of time series, record of data as a function of time. And that's something I'll be talking about today. So anyway, and a lot of my teachers were from the French Navy Hydrographic and Oceanographic Services anyway, that were also located in Brest, in Brittany. And I'm just putting a plug for a book that is actually on my reading list by a historian of science, Naomi Oreskes, who's now at Harvard, who wrote a book about how, the military has shaped what we know and what we don't know about the ocean. So at least at the beginning, I believe that's true. So then I went on to do a PhD, as Nick said, in Scripps Institution of Oceanography at the University of California in San Diego, in Southern California, very much at the border with Mexico. And on this historical photo from the first building of that laboratory in 1911, you can see how Southern California was basically a very arid, desertic area that was also facing the ocean. And it turns out that Southern California is the same type of environment that Mauritania, where I was born, where you have this very arid land facing a very cold ocean, but nevertheless, which is very rich in nutrients and ecosystem and fish and activities. Anyway, so this is a more recent picture showing where my office was for about 5 years, just facing the ocean. But when I started my PhD, I was lucky to joined a program where I didn't have to pick an advisor at first, and I didn't have to pick a topic of research for about a year in order to make a match, a personal match with an advisor, and in order to figure out what I wanted to do. But I was lucky because I'm paraphrasing my advisor at the time, who told me, at the start of my research, he said, why don't you look at this data and see what you can find? And so, maybe we don't like as scientists to frame our research this way, but that's how it happened. And a lot of times, behind the curtain of our proposals that we write or the way we present ourselves, we're pretty much dealt with data, and we have to try to figure out what to do with it. So then, I'm going to fast forward a little bit. As Nick said, I got my first job as a scientist in Miami. I went to England, and then I moved back to Miami in 2013. I worked at RSMAS as a scientist, and I joined the faculty in 2019. And since 2016, I've also been a research associate at the Carnegie Museum of Natural History in Pittsburgh, Pennsylvania. So I spend my time between Miami and Pittsburgh. So I was asking myself, when I was being asked to give this talk, like, am I a data scientist? And maybe that has to do with the type of science that I do. So I had to think a little bit about it. So, I did some search, and Wikipedia led me to, a quote from the proceedings of a conference from 1996, almost 30 years ago, a paper by Shikio Ashai that said, data science is not only a synthetic concept to unify statistics, data analysis, and their related methods, but also comprises the result. And it includes three phases: design for data, collection of data, and analysis of data. Well, that's actually what I do. I plan expeditions to go at sea. I collect the data at sea, or I make sure I rely on autonomous instruments, and then I analyze the data. So yeah, that works. I'm a data scientist in that respect. But then I couldn't help, I keep reading about it, and a more recent book by a couple of authors from the Rotary collection. And if you don't know that collection, it's very delightful if you're a scientist or a data scientist or an engineer, and you try to get into technical stuff. All these books are actually available from the University of Library. And I found this quote which says that the reality is that currently no one calls themselves a data scientist in academia, except to take on a secondary title for the sake of being part of a data science institute at a university, or for applying for a grant that supplies money for data science research. So once I read that quote, I was just laughing for a minute, and you can draw your own conclusions from that. But how do I describe myself? So I deal with, I'm lucky to meet a lot of people that are not scientists, that are not oceanographers. But in general, I describe myself as being a scientist that uses data to come up with descriptions about the working of the ocean. Its inner working, how it works intrinsically, and how it's being forced, how it's changing because of climate change, as an example. So I'm not much of a theorist, outside of a few exceptions. I've published a couple of papers that dealt a little bit with theory, but mostly I try to verify, or rather invalidate, existing theories in physical oceanography. So very smart people came up with theories, and then I have a bunch of data. I'm going to say, you know what, I'm going to test that theory and to see if my results are compatible with that theory. Then you can say, well, maybe we cannot invalidate yet that theory because the data or my analysis of the data seems to be compatible. But I'm also data-driven. That is, I've been dealing with a very big data set, very big for me, and I'm trying to understand what it means. I'm trying to understand the information that we're getting out of this data set. So I'm also data-driven in that respect. So the way I thought about it, so I'm a research faculty, meaning I don't teach at the University of Miami, but ironically, I have taught in other universities, such as the University of Cape Town. I taught in the Department in Oceanography, and I conducted a 1-week-long course on methods of data analysis in oceanic and atmospheric sciences. But my first lecture on the first day was called Essential Statistics. So why did I give such a lecture is because I told the students, and I'm going to go through a little bit of my lecture here. I said, well, let's look at the definition of statistics. It's a branch of mathematics that is dealing with the collection, analysis, interpretation, and presentation of masses of numerical data. So once again, that's what I do every day. Or, one day I do one, the other day I do the other one. I do that all the time, dealing with my work. Or another, definition is that it is a practice or the science of collecting and analyzing numerical data in large quantities, especially for the purpose of inferring proportions in a whole from those in a representative sample. So basically, you observe a small part of a data set, or you reduce it, and you try to make conclusions about the whole, which is pretty much the struggle that we have in oceanography, where we cannot observe everything. So in oceanography and atmospheric science, we have at our disposal a number of physical theories, that is, equations that describe the spatial and temporal variability of the climate system. And so specifically in geophysical fluid dynamics, that is the dynamics of the ocean, the atmosphere, we have the Navier-Stokes equations that are describing the motion of fluid. Yet we do not know to this day if these equations, we know that they are appropriate, but we do not know if they have actually reasonable physical solutions. If you figure this out, there's actually a $1 million prize from the Clay Mathematical Institute. So, but assuming that these equations have reasonable solutions, whatever that means, then the ocean can be seen as a deterministic system. Deterministic means that you can just use a mathematical expression to describe completely its properties. That is, you want to know the velocity of the ocean or like the shape of the pressure field. You're just going to say that the pressure, P of X and T, position and time, is a function of, let's say, a cosine function of position and time. That's deterministic. Yet, even if we don't know what the analytical solutions are, we can nevertheless discretize the equations within a computer model to obtain approximate solutions describing the flow deterministically. So we don't know what the analytical solution is, but we can use a computer to describe what the flow is going to be, in theory. However, a deterministic approach to the ocean problem is not realistic because of three reasons. So the ocean or the atmosphere is complex, it's nonlinear, and it's unpredictable. As an example, it is estimated that there's about 4.7 times 10 to the 46 water molecules in the ocean. That's complexity for you right there. There are too many variables. There are too many initial and boundary conditions to be specified in your equations. So all these particles, all these initial conditions are the degrees of freedom of the system, the number of independent variables. So we cannot solve all these equations for all these particles in a computer model. So we have to choose some of the particles we're going to model, actually. So we cannot observe all the variables. And so we cannot specify everything. So when we look at the outcome of a numerical model, it's going to appear random to us, as if by chance. So that's the unpredictability of the system, basically. And then finally, one way of seeing the system as being nonlinear is that we cannot find a small portion of the system that we can reduce to a finite number of particles that we could track, let's say, or a finite number of degrees of freedom that we could track. And so this is what we mean nonlinear in that case. So an unknown number of perturbations are going to render the observations, as if they were created by chance. So this is noise, this is randomness for you. So once we accept that the ocean and the climate system is not purely a deterministic system because of its complexity and its nonlinearities, but contain randomness, we can rely on a suite of tools that are applicable to this randomness, to this chance character of the data that we observe in the ocean. This type of system is called stochastic or random. So as a consequence, data scientists like myself, especially in oceanography, we study random variables, that is, variables to which we can apply statistical theories. We can apply the theory of statistics. So, and often what we say is that we have a signal, and then everything else that is not our signal of interest is noise. All right, so with that, that's a little bit my philosophical approach to what it means to be a data scientist in oceanography. And so in the rest of my talk, I wanted to tell you a little bit about some of the work that I've been doing, or some of the approaches that I've been implementing to deal with my work. So one way we have as oceanographers to observe the ocean is to deploy in the ocean buoys that are going to be able to drift in a free manner at the surface of the ocean. So that buoy is going to drift at the surface of the ocean, and it's going to follow the flow. It's going to observe the ocean as the ocean is moving at the surface. So that this is what the oceanographers call a Lagrangian perspective on observing the ocean, as opposed to an Eulerian way of observing the ocean, which is observing the ocean at a fixed place, looking at the water passing you by. So you're going to follow the water. So on the right, you see a couple of photos that I took on a ship back in the Aquilus Current in 2018, where we had some students on board deploying one of these buoys that we call drifters. And here on the right, you have a diagram of what a buoy looks like, a drifter looks like. It has a buoy at the surface, which is tracked by satellite, so you know its displacement. And it has this very long, elongated type of sock with hole in it that is basically pushed by the currents at a depth of about 15 meters. And as it's being pushed, advected around the ocean, the trajectory of the buoy at the surface is tracked by satellite. And so you're going to assume that the displacement of that buoy at the surface is representative of the currents at depth. So this type of buoy in that instance is part of a program called the Global Drifter Program, which is mostly funded and coordinated by the NOAA here in the US with international collaboration. And the goal of these buoys is to observe ocean currents, sea surface temperature, as well as the pressure of the atmospheric pressure at the sea level for some of them. So we can observe the ocean. So as an example, this buoy was released between the islands of Cuba and Hispaniola, and then it follows the path given by this little plot here. As you can see, we call that a spaghetti diagram, because basically it looks like a bunch of cooked noodles that you would just like have on a table. And so you can see that this buoy drifted through the Yucatan Channel, got trapped into the loop current in the Gulf of Mexico. Some of you may be familiar. And then it passed by Miami, said hi to us, and went through the Straits of Florida. It was embedded into what we call the Florida current, but which is actually the Gulf Stream. And then it drifted north all the way to Cap Hatteras. And then it started to go inside the Atlantic Ocean. And then it did this crazy thing. It just looked it around. And then it went around and joined the North Atlantic current, and then died in the middle of the Atlantic and stopped transmitting its position. So a number of my colleagues and I have been using this drifter as a test case, and we gave it the name Betty for some unknown reason. And it traveled from October 2004 to May 2007 for about 944 days. That was a very good life for this drifter. And it traveled 33,000 kilometers across the North Atlantic. So you can deduce the direction of the currents. And by the way, I'm sure you understand why we want to know why currents needs to be observed, why they are important for us. But basically, the currents at the surface are going to be responsible for the drift and the dispersion of all suspended animate and inanimate matters. So ocean currents is basically the most important variables that you need to model or you need to predict in a computer in order to actually predict the fate of pollutants that threaten ecosystem and human health, such as plastics, oil spills, radioactive isotopes, chemical compounds, or even people. If they fall at sea, you want to know where the currents are going. So you may want to have a chance to save them at sea. So you have this trajectory and it tells you what the currents are doing, but then you can zoom a little bit on it. Then when you zoom on it, it's a little bit fractal in the sense that you see that the trajectory of these buoys is doing big loops going around. You wonder what's happening, but then it's doing some smaller loops, as you can see in this part of the trajectory. And then it's doing some even smaller loops at this part of the trajectory. So now you start to wonder, well, the current is acting on very different spatial and temporal scales. Is there a way by which, looking at this data, we can actually quantify this motion in the ocean? So one way to look at this is that from the displacement of the buoy as a function of time, you're going to deduce the velocity, that is the surface currents. And you're going to look at its component going east-west, and you're going to look at this component going north-south. So east-west is typically what we call the component U, the zonal velocity. And north-south is going to be the component V, which is going north and south in red in that on this plot. So it's a record or time series of these two quantities as a function of time. And here I'm showing you a little zoom between days 220 and 300 that shows that you have this very regular oscillation of the current at this time. So here, this time series has two components, a U and a V component. And so basically it's what we call a bivariate variable in statistics or in data analysis. So now we can ask the question, how much energy or what is the size of the current as a function of time, as a function of time scale, or equivalently as a function of frequency of the motions. So one way to look at this is once again to consider that this time series as a function of time has two components. And if you talk about the east-west or the north-south components, we call them Cartesian components. And it comes from the work that was done in geometry by a guy named René Descartes, a French philosopher and mathematician from the 17th century. And he came up with this representation east-west, north-south. So another French mathematician and theorist, Joseph Fourier, from more like the 18th and 19th century, came up with a theory that is telling us that if a time series, a record of data as a function of time is periodic with time, that is, it repeats itself, then you can decompose it mathematically into what is now called a Fourier series. That is a sum, an infinite sum of an infinite sum of a number of cosine functions with different amplitudes. That is a set of basis functions that are going to describe regular oscillation in a time series. So we have mathematical ways to get the amplitude and the phase of those cosine functions. And as you determine the phase and the amplitude of these cosine functions, you conduct what is called a spectral analysis. And so you're going to calculate all the components of that spectral analysis for the zonal component and for the meridional component. And then you're going to look at the magnitude of those coefficients as a function of time scale, as a function of frequency, if you want. Once you do that, for the record that I showed you previously, you obtain what we call a velocity spectrum. And a velocity spectrum is basically giving you the energy in the ocean, the mechanical energy in the ocean, which is something we really want to know. And so here on this plot, you see such a spectrum as a function of frequency on the x-axis and an arbitrary level here on the y-axis that give you the energy level. And we have this energy level for the zonal component in blue and for the meridional component in red. And what you can see is that the energy level is higher at low frequencies. That means that, so it means that you have the most of the energy at long time scale in the ocean. And we're talking about time scale of 10 to the minus 3 to 10 to the minus 2 cycles per day, which means 1,000 to 100 days period time of oscillation. And you can see that this is where you have the most energy. And then you can see at high frequencies, let's say 10 cycles per day, very fast motions, you have less energy in general. This is a general characteristic of the ocean. But you can see that you have some bumps in that spectrum, and colloquially, they are called peaks. And you can see that you have some higher level of energy here, around 1 cycle per day, as well as higher level of energy here around 0.3 cycle per day, about 3 to 4 days time period. And what we know in the ocean is that there's a preferential frequency of oscillation in the ocean called the Coriolis frequency, which has to do with the rotation of the Earth. The rotation of the Earth leads to a force at the surface of the ocean called the Coriolis Force. And once again, due to a French scientist called Gaspard Gustave de Coriolis from the 19th century that derived the equation that shows that the rotation of the Earth is influencing motion at the surface of the ocean and in the atmosphere. So you have this peak here that occurs in the ocean. And then you see there's another peak that occurs at another frequency. So what can we say about this? So alternatively, there's another way of describing a time series, a record of data as a function of time when you have a bivariate time series. It can actually be decomposed instead of the Cartesian component in zonal and meridional. You can decompose it into counter-rotating components, into circular components. And this is what is called a rotary spectral analysis, which is one of the tools that I've been using for a very long time to study the ocean. And you can conduct the same, you can calculate the spectra of the rotary components. So how does that work in practice? So here I'm showing you a toy example, these little animations, where you have a velocity time series that is shown here by this arrow that changes as a function of time. And then actually I created this synthetic time series, this velocity, this vector, by summing it as the sum of 4 components that are rotating counterclockwise and 2 components that are rotating clockwise. So it's a very purely mathematical decomposition of the signal, but sometimes in the ocean it has a straightforward physical interpretation to it. But when you sum those 6 components, you get the result that you get here. So now applying a spectral analysis to a vector time series, considering rotating components, is providing you with a decomposition as a function of frequency or as a function of time period into circular motions that are rotating in one direction or in another direction. And why is that important in the ocean? Is because of the following reason. So when you do this, when you decompose the same time series from that drifter body into positive components that are cyclonic in the ocean, that means counterclockwise in the northern hemisphere, and negative frequencies that are anticyclonic, which means counterclockwise, sorry, I said the same thing, but are clockwise in the northern hemisphere, you get the results here. So what do we find? We find that the peak in the spectrum at low frequency is entirely contained for positive frequencies. So what did we have? We have identified actually an ocean cyclones. So just like in the atmosphere, you have cyclones and anticyclones, we have the same in the ocean that we have in the atmosphere. So we call that an eddy. And we found that it was purely cyclonic. And then we found that this inertial motion at the Coriolis frequency were purely anticyclonic, which means that in the ocean, in the northern hemisphere, they are actually clockwise. So applying this different type of decomposition in the ocean allowed us to understand if the motion, the currents were looping in one direction or the other direction, which is telling us something about the way the ocean works. Just like you look at your weather forecast and you look at cyclones and anticyclones, on your weather map, we also have cyclones and anticyclones in the ocean. And this type of analysis is allowing ourselves to see that in the data that we get from these buoys. So what do you do with that? So you repeat the analysis with 17,000 drifters, which is the entire data set that we have right now in the Global Drifter Program. And it amounts to about 165 million data points of estimated velocity. And so this is where the complexity of the system and maybe, you know, the application of like data science comes in, because you have to deal with all those records of time series. So when you do this, and then you analyze and you calculate a spectrum, a rotary spectrum, as a function of latitude and frequency in the ocean, you come up with such a representation of the energy in the ocean. And you can see that you have a lot of energy at relatively low frequency, which is present here. And then you have a lot of energy that is following this curve here, which corresponds to that inertial frequency that changes size, that changes magnitude and frequency as a function of latitude in the ocean. And then you see those stripes in the vertical at 1 cycle per day and 2 cycles per day. And that corresponds to the ocean tides, the tides in the ocean. And you can actually see that also in the trajectory of these drifters. So why does it matter? Why do you do such things? So one of the things you can do is that, you know, we're trying to understand the way the ocean works. We're trying to understand the climate. We're trying to predict the climate. And by the way, the climate is the atmosphere, the ocean. It is the biosphere, all the living things, and the cryosphere, which is the frozen ice on this planet. So definitely the ocean is one of the integral part of the climate system. So we want to try to model it. So as I said, it's very complex, but we use numerical models. We use ocean models. So here on the left, I'm showing you an animation from an example of an ocean model that is run by NASA, which was originally written at MIT. And this is a visualization that is available that shows you a snapshot every day of that numerical models for 1 year. And so what I did with my colleagues is that we applied the same type of analysis that I described to you to the output of these numerical models. So these numerical models, we're talking about 10 terabytes of data, which is something I cannot do on my laptop, which is something I cannot do even on my desktop. So through, you know, funding that I obtained, I was able to buy into the high computing performance system at iDisk to be actually able to analyze the output of this model. It was actually another model called HiCom. This model was analyzed by my colleague at the Jet Propulsion Laboratory in Pasadena. And so that representation of the spectrum, of the energy of the spectrum that I showed you earlier from the drifters, you can obtain the same representation in the models for the HiCom model at the surface and at 15-meter depth, or in that MIT model at the surface and at 15 meter, which is that model which is on here on the left. So now we can compare the truth, what we think is the truth, those buoys, to what is actually being modeled by these computer models, and try to see the differences, if they come from problems in the models, if they come from problems in the data, and trying to understand and compare the two to try to advance the modeling and predict better the ocean and thus the climate. And one of the things you can do is also you can look at this time series, this data, and then you can extract some specific bands of motions. As an example here, let's say we're going to extract these motions at that natural resonant frequency of the ocean. So you're doing a bandpass on that time series. You can do it also for the tides, and that's another project that I have currently funded by NSF, which is to map the tidal currents in the ocean. And we need to do the same thing in that computer model that I've shown you as well. So I'm using the resources from my disk to do the same thing. And one of the things that we do is that we map the energy of those tidal currents, which are shown here. And I could talk about this. I'm writing a paper to describe with these results, but I'm trying to answer a question such as how variable are the tidal currents in the ocean, and how spatially and temporally variable are they? And so it's only by applying this type of methods that I described earlier that you can get such maps and get a global picture of, let's say, the variability of the tides in the ocean. So what else can you do? So I wanted to go back to what I said at the beginning, that I was born in that town called Nouadhibou, and I was telling you that unfortunately some migrants were trying to depart on very small raft to try to reach the Canary Islands in Spain. And I was actually contacted by a journalist a couple of months ago, and I was not able to help her because, often I get contacted by people trying to ask me for my expertise, and they're actually asking me to do a study for free for them. And I have to tell them, I'm sorry, but I don't have the time to do this. My time is precious and limited. But, one of the things we can say is that we can use, let's say, the buoys and to try to look at the average currents. To try to see on average what is the direction and the strength of the currents. And so this is some work that has been done in the past by Lucas Lorindo, who used to be a student here at RSMAS at the Rosenstiel school. And he applied some methods to look at the average current. And so if you zoom a little bit on the western coast of Africa, it's a little bit smaller, I apologize, but where the point of my cursor is, you would see that blue shade of currents that are going north and south. And blue means that the currents are basically going south in that region. And then if you look at the east-west component of the currents, it's basically telling you that the currents are going towards the west. So these migrant people boarding ships in Nouadhibou are trying to get north towards the Canary Islands, but the currents is likely going to bring them south and towards the west. And unfortunately, it has been found rafts with, unfortunately, dead people in the Caribbean, because they rely on currents and they rely on chance to actually reach the Canary Islands, but it's not a very good path to reach the Canary Islands from Nouadhibou, and we actually know that from our knowledge. All right, but what about, you try to answer scientifically driven questions, but what about data-driven work? And so I'm sorry, I had to plug this, diagram from the Berkeley University School of Information, trying to describe what data science is. And so I looked at this diagram and I looked at processing data. All right, I do that. Analyze data, I do that. Communicate data, write papers, give you a talk today about it, I do that. Capture paper, yes, I do capture data. I go on ships or I throw instruments in the ocean and I hope to get them back, or at least their data. I do that. But what about the maintaining of the data? So it comes from, being a statistician, an oceanographer. Sometimes in the past, I've got frustrated about the accessibility of data or the format of data. So I started to wonder, is there something more I can do, upstream of what I'm used to do, or let's say as part of this cycle, to foster better description stewardship of data. And so it turns out that oceanography has entered the realm of big data, which is maybe something you heard about in some other field. So here's an example. We have, through a coordinated organization called the Global Ocean Observing System, we coordinate all the observations that we obtain at any day. And here I took a screenshot from just the Pacific side of the ocean that shows you yesterday all the observations just from autonomous or ships or robots that we have in the ocean that are observing the ocean every day. And this system is generating 1 million new data points of observation every day. So the data sets are growing too rapidly, and the software we've had so far on our hands to analyze this data set are not able to keep up with the increase of data. So some of the fields have done much better, but in oceanography, we still need to do better in atmospheric science as well. But there are some community and agency-funded efforts that are being put in place to deal with this growing amount of data in order to make it accessible much more rapidly to the scientists in a format which is practical and which is meant for analysis, basically. So as part of this thinking, I was lucky to be funded through the EarthCube program of the National Science Foundation for a project which I call Cloud Drift, which is a platform for accelerating the research with Lagrangian climate data. So Lagrangian data, remember, is this type of data that are following the flow that I was telling you about. And so hopefully, I've been working on this project for a few months already with some colleagues at Florida State University as an example. But this project will help scientists and non-scientists to utilize Lagrangian oceanographic data by providing access to tailored cloud-based data set and software. And so this is what I was trying to represent here, where we're going to try to take this data coming from many different sources and format them into an analysis-ready cloud-optimized format, put it in the cloud. And what does a cloud mean? It means a non-centralized area where you're going to have both storage and computing capabilities that could be accessed instantly by a very wide and large number of individual computers or individuals that want to access this data without having the need to actually download them or maybe rely on supercomputers that are, within the walls of big universities. I have another project that I wanted to talk about very quickly, is that this increasing amount of data that we have in oceanography is great, but there's one thing that we need to do better is to quantify the quality of this data. And basically it means quantifying the errors that are associated with the data, like the uncertainty. Because when you want to analyze data, you want to know how good they are. You want to know how reliable they are to do the analysis that you want to do. And even if they're not very good, it's all right. It's better to have data, it's better to have data than not have data at all. But you want to know how good those data are so that you can put error bars and quantify the uncertainty on your analysis. So as part of this initiative, I'm leading a working group that is funded by a climate variability program. And it's a working group called the Ocean Uncertainty Quantification. And one of the things that we have to do, it's a group of experts, about 12 experts a panel, and we think about these things. One of the things is we write papers and alert people of these issues. And we recently submitted a paper. We recently published a paper in the newsletter of the American Geophysical Union, where the main point is basically the data are made complete if they are accompanied by an uncertainty quantification, which simply means that I'm going to tell you that this ocean current is 1 meter per second, but it could be 1 meter per second plus or minus 5 centimeters per second. And just having this added information really increases the value of your data. So it's problematic because now it can be problematic because now you need, let's say, a terabyte. You're going to produce a terabyte of data, but most likely you're going to have to produce another terabyte of data that are just going to qualify this data set. So you can see how it's linked to having to deal with big data and having to deal with new ways of dealing with data science. All right. So I talked to you about a lot of different things today, and I hope I give you a few ideas of the things that I'm concerned with and I'm talking about. And with this, I'll stop here. Here's my email if you have some questions further on. I have a website also where I have my some description of my projects as well as some my lectures on statistics. And you can follow me on Twitter as well to follow. Thank you.
Great. Thank you, Shane. Very stimulating talk. I really enjoyed it. So do we have any questions for Shane? Does anyone want to start, our discussion? We have about, 10 minutes, 10, 15 minutes, I think, to ask questions for Shane. We have any questions? Anyone who wants to put either, unmute yourself and ask a question, or you can enter it in the chat.
Hi, Shane. It's Amanda Myers. That was a really nice talk. This is a little bit maybe far afield, but we live in Miami. We have huge flooding problems. Are you using these models? You talked about potentially helping people figure out where immigrants were drifting and how that works. Are you using it for any sort of city planning? I was reading about Brickell is trying to decide between doing a seawall or doing mangroves. I imagine that your models could really feed into that kind of math and be extremely helpful for figuring out, what's the best solution to those problems. Yeah. Thanks so much for your time.
Yeah, of course. So you talk about the models, which is a very good point. So these are not my models. These are models that are run by communities, and anybody can analyze them, thankfully, if they have the tools to do so. So the type of models that I talked about today are very much, skilled. They are very much designed to look at the currents that are being depicted right now in this animation, right? And so these type of models, or even models that are trying to deal with what's happening at the coast, are actually not yet very good at modeling the changes of sea level right at the coast. So they're getting better, but right now they're not as good. They're not as good as they should be. So there's a real effort by the community, not by myself, to actually increase the skills of these models to predict, to help the flooding. But looking at the currents are very important. As an example, we do know, and there are several scientists here at the Rosenstiel School and at AOML that are specifically studying the impact of the Gulf Stream onto the sea level in Miami. And there's a number of projects that are on the way to look at this, because for some physical reason, the strength of the Gulf Stream flowing in the Florida Straits is actually directly impacting the sea level in Miami. So that's one thing. And the other thing I didn't talk about today, which is also very exciting for me, is that those drifters that I told you about are actually tracked by GPS. And they've been tracked by GPS for not too long, actually. They used to be tracked by another tracking system. And so the great thing about GPS is that you can actually measure altitude, right? So you can actually measure, technically, potentially, theoretically, the height of the sea level that these drifters are flowing on, right? So, if you were actually, able to walk on water, like someone we know, you would be able, if you were to walk from Miami to the Bahamas, you would be actually going up a hill of about 1 meter high, right? That's because of the way the physics of the ocean is working. So if you had a drifter that was going from Miami to the Bahamas, technically, if it had a proper GPS, you would be able to measure that height. So long story short, I have a little project with the Jet Propulsion Laboratory to actually find the adequate technology to measure sea level with those drifters. So that type of work would help towards better prediction, basically, of the sea level in Miami and everywhere in the world. And the idea would be to turn this array of drifters that I'm using for a lot of my work into another way of measuring sea level. And I also, so I'm trying to design a new observing system. And, lucky for me, I just got the Provost Research Award as well recently to run some experiments on a number of models as well, and to do some buy-in actually with the HPC at IDIS to actually generate synthetic trajectories of drifters in computer models and simulate the type of sea level measurements they're going to obtain in order to better devise this new observing system that I envisage would be useful to help with measurement and prediction of sea level. That was a very long answer to your question, but yes, sea level is very much on the mind of a lot of scientists.
My question was far afield, so I really appreciate the very long answer. It's really interesting stuff and very crucial stuff. So thanks so much.
Thank you.
Great. So Shane, I have actually a little bit of a comment and a little bit of, I would like your thoughts. I mean, actually you described very well actually what data science is all about, and you showed a little bit of the trajectory, if you will. That doesn't necessarily mean that data science is not using statistics or, other kind of methodologies, math and so forth. But what I found extremely interesting actually, and I would like you to comment a little bit, is that, you have the more, how can I say, model-oriented simulations, right? What we call it the computational science approach, and then the data-driven science, where you are using the data from buoys and other kind of sources. And can you actually elaborate a little bit in that in your field? You showed a couple of things of how the real data from the buoys match with the models like HiCom and the MIT model. But can you elaborate a little bit about that, of how the distance of those two is, and how much, it's actually coming together, and, because that's actually a pretty interesting topic in many other areas and fields as well, about more of the computational models and simulations, if you will, versus actually the data driven. And now we can get a lot of more data. Before we couldn't, right? And we needed to be able to model a lot of the physics, if you will, in this case, but in other cases, other kind of aspects, where now with the data, how do you think that this thing, these two aspects are, converge, if you will, at some point?
Yeah, no, I think this is a very good point. So, so I didn't go into the details of this comparison between the drifters and the model, but, one of the things I say when I talk about this results that, we submitted for publication is that we're comparing the drifters, and then we're comparing a model called HiCom, and then the MIT GCM. So it's like orange to apples to bananas, basically, right? Because each of the source of data has different characteristics as well as different uncertainties, right? Or errors, right? So they don't represent the same thing. So the main thing, and that's going to be the next step in this research project, relying as well on, on the Triton supercomputer for me to do that, is related to what I was telling Amanda. So, this type of representation of the energy, the kinetic energy spectrum as a function of latitude and frequency, was basically obtained through this Lagrangian approach, which is basically following the flow, the trajectory, right? And then, but for the model, we didn't do that, because the model is providing you with velocity always at the same grid point, the discretization of the model as a function of time. So we use slightly different, we use same statistical methods, but we use different type of data. So that's one of the things that is a caveat of this study, because we use different ways of sampling the ocean, either the real ocean or the numerical ocean. So the next step is, so one of the things I say to people, they want to come to my office and say, oh, you're an oceanographer, I want to see what you do. But what I do is basically I sit most of the time in this office. So that's not very exciting, because my laboratory is the ocean, right? So it costs a lot of money to go in the ocean. Like one of the ships I go on costs about $20,000 to $40,000 a day to run, right? So I don't get to decide to go to the ocean on a whim. So we use those digital twin of the ocean, which is a model. So what we're going to do as a next step, we're going to release synthetic particles in the model offline. So I'm going to use that model, and I'm going to release synthetic drifters, millions of them, in the model. I'm going to save the data, and then I'm going to get trajectories of those particles in the model, and I'm going to analyze them like the drifters. By doing so, I'm going to be more like comparing more like, oranges and tangerines, right? It's going to look much better. The comparison will be more fair. So that's the first thing, the next step. And I think it answers a little bit your question, because we're trying to find new innovative ways that really needs to, use very, innovative and inventive tools to be able to deal with the amount of data, but to try to simulate the observations that we obtain in the ocean. Does that answer your question a little bit?
Yes, a little bit, yes. I think that I understand, but also what you are saying is that, well, we still have the gap that we need to bridge, right? Because in many cases, we are not really modeling even the same thing.
Yes.
Although at the end of the day, we want to understand the movement of the ocean, right? So
yeah,
at the end of the day.
Yeah. And so another thing, to answer your question, so comparing different type of observations, right? And this is the type of things that as part of this, working group on ocean uncertainty quantification, we've been thinking about. One of the things that is very important is sea surface temperature. And, I see Melvin is here online, and we've had a project together where we're trying to understand, the patterns of sea surface temperature at the surface of the ocean. And so we observe the temperature at the surface of the ocean with these buoys. They actually have a temperature sensor attached to the buoys. And a lot of people are comparing this data to estimates of sea surface temperature you obtain from a satellite, as an example. So these are two, physical measurements of the real ocean, but a satellite is basically it used like a passive inframeter that is like measuring the radiation from the surface of the ocean. So it has an imprint of maybe, several kilometers wide. And then that buoy is about 40 centimeters wide, right? So you measure the temperature over the footprint, which is several kilometers of a satellite, and you compare it to a pointwise measurement from that small buoy. So then you compare the two and they don't match. And then you call that an error or an uncertainty in one measurement or the other. So then it becomes an exercise in trying to think about what is the representativeness of the data.
Right.
Or another way to put it, what uncertainty can be quantified, what uncertainty can you put onto that representativeness of the data that would make it for a fair comparison between a model, in situ observations, satellite data.
Wonderful. Okay, so we are actually at 5, and I think that if there is no other question, I would like to take the chance to thank Shane for giving us this very engaging and inspirational talk, and I would like to thank everyone for being here today.
Thank you very much for your time.
Thank you all, and thank you, Shane, again.